So yes, today we're talking about avoiding traffic, or a method to avoid traffic. It'll be a little bit schematic. We're not quite going full Google scale. I'll elaborate on that in a second. But it'll at least be a good exercise. We're going to look at quite a few different things in some level of depth. As I just said, we're going to do a little bit of computer vision, which in Mathematica, to be honest, is so easy. We won't notice that we're using computer vision. But we'll do some computer vision. We'll do a little bit towards the end, like a little bit of linear algebra. We'll do some graph theory. There's a more obvious graph that appears here, right? We're going to like model London as a series of junction and roads, so that's a graph. But there's going to be a second graph that will surprise us at some point, so we'll do with that, and so on. So here's the outline. We'll start with the introduction, which is now, and then we'll set up the question in a little bit more detail than what I just did. And then we'll start to look at the data that we have, and it'll immediately turn out that we need to wrangle with this data a little bit. This data is not yet close to what we need. So we'll look at the data, we'll see what it is, we'll deal with it, and then we'll explore the data. For example, we'll build a traffic map within the first few slides of London from over here in Oxford, or I guess a lot of you guys are in America. We'll analyze. So this is when we start, looking for shortest paths, basically trying to avoid traffic. Communicate, in the sense that we're going to build at the end like a little interactive application where you pick two road names, and then it'll give you the shortest path, or the most traffic-free path between those two things. And then we'll summarize and hopefully go home and have a great weekend. For me, I'm going hiking with my brother, so I'm excited for that. Anyway, to the actual work that we have to do. We are going to use, as we just indicated, a few different tools from different domains in order to discover how to commute around London whilst avoiding traffic as much as possible. So I want to be precise about the actual problem that we're solving here. What we're doing is finding out how to travel around London somehow as antisocially as possible. We're trying to minimize the number of faces that we see. We aren't necessarily minimizing the transit time. That's a different problem. Although I would say that it's probably highly correlated, right? The more traffic there is at a junction, the slower it's going to be to get through it. But what we're doing is, yes, just minimizing the number of cars that we come across. The other problem is slightly harder. It's not what we do today. So that's the question. That's the problem. How do we get around London whilst avoiding traffic? To answer that question, we're going to have to answer two smaller questions. Right? The first thing is, okay, how do we know what the situation is in London in terms of the traffic? How do we get that impression in the first place? That's the first thing we're going to have to find out. And then secondly, how do we model London as a graph, right? And just to be explicit, what do we mean by a graph here? Because a graph has like a few different meanings. What we mean by a graph is an abstract model of like the structure of London. So we have the junctions, like the intersections, and then the roads between them. So those are our dots and our lines. So we have to solve those two problems, and we're going to do that now. I want to reiterate, please, especially if you're on Big Market, feel free to ask loads of questions. Feel free just to make remarks if you have any. I see we haven't already, so that's great. There's a lot of people daily using this kind of strategies to commute, and how does it affect the predictability of the model? That's a good question. So I'd say definitely a lot of people are using this kind of strategy, but not necessarily for the commuting. So I'll just start off. I think I've already admitted that Google will solve this problem better than we do. Why is that? For a bunch of reasons, obviously. One of them being that they have access to different data. What we're going to do today is take pictures of junctions and count cars, okay? Because that's the best that I could think of off the bat. What Google has is different data, right? What Google has is like the actual time it takes, people using Google Maps to get through a junction. They have sort of really useful data there. They know like the actual amount of time it takes to get through a junction. We don't know that. And I'll indicate briefly how you could figure that out, but we don't do that. In terms of the strategies, like some of the strategies I'll show you are used all the time in lots of different domains, and I'll try and point out like when that's the case. But in terms of for commuting, the shortest path thing that we'll see, that's definitely used all the time. But if you were going to solve this problem for real, like Google does, you'd want to start off with different data, maybe do slightly different things. But there's definitely going to be a lot in common. Okay, so we want to get an impression of the traffic in London. And here's where we start. This is a government website here in the UK. It's Transport for London. They very kindly provide this API, which provides data about the so-called JamCams. So these are just traffic cameras. They're not already. So I run that. It imports. This is going to. This is like it's calling an API, so it's going to get a JSON response, and I say import that as raw JSON. That converts it into like an association into Wolfram Language form. So I do that, and I'm sort of like immediately horrified at the response. The response is not like a normal JSON response. What happened is I think they have like objects in a different language and they serialize it without doing much work. And they don't need to. That's our job. So here's where we start. It looks a little bit complicated. It doesn't quite fit. I think a good idea in something like this, if you have a list of things that you want to understand, is just to start with a random one of those. Take a random thing, and you have a look. See what you can figure out. So here I took a random point, and it's still a bit too big. So what else could we do? We could also take the keys, just to see like there's an association that goes from keys to values, and we want to see what are the keys that we have. So we can just say take the keys. Okay, type. We don't like the type and the ID is not useful to us, but there's a few things that are useful. The latitude and longitude, right? That's the position. That's where the camera is. We want to know that for sure, so we'll keep that. The common name, that's also useful, right? And if we squint, if we stare at this thing, we see, oh, we're also after this thing. This is a picture. We can import it, although it's on the internet. This is what we're after. Okay, this is the next thing that we're after. This is how we're going to count cars. It's from this picture. But it's given to us in a bit of a strange way, where like the value of the key is pointed at by a key called key. So it's like, okay, we want this thing. How do we get it? We have to look in additional properties, which is a key at the top level. Additional properties, which gives us a list of things, a list of additional properties, I suppose. And then we want to find the additional property that has this, which is going to be the additional property where key goes to image URL. So first of all, I don't even know if every one of these JamCams has an image attached. So the first thing I do is select from the endpoints, which is this JSON response we just got. Select from them the ones where any of their additional properties have a key set to URL. So these are the ones that we know have a JPEG attached. That's what we know about these things. Okay, and then I want to sort of dig out that JPEG. So I write like a little function here, and it's what it does is it takes something like this, and then it goes to the additional properties, and then it selects the first, because the additional properties is a list. So it selects the first thing in that list that has this image URL, which hopefully is the only thing, and we take the value. Okay. It seems a little obscure. I agree, it sort of is. This is not how a JSON response is usually formatted. But you may have to deal with stuff like this, right? So this is if the data you're dealing with is messy, then the solution might seem a bit messy as well. We have to do some sort of digging essentially to get out eventually what we get here. So what I've done here is I've begun to format our data in a way that's much neater. So these are our endpoints with images. And I said we'd like to keep the name because it's useful to know the road names. The snapshot, this will be a picture, and that's, well, at the moment this is going to be the URL of a picture, and this will point to that URL. The position is going to be a geo position. So this is Mathematica's conception of a geographic location. It's a latitude and longitude. And so I map that over our data. Okay, so we're in a better situation now, but not a perfect one. We know that all of the things that we've just made have a picture involved, but not all of those pictures are useful. Sometimes for a variety of reasons, right? A camera is offline. And with this data stream, when the camera is offline, the feed doesn't go away. It just looks like this. So we would like to not consider this in our data set. We'd like to delete these things. We have to detect when a frame looks like this, right? And we can't just check if it looks exactly like this, because different cameras have different names. And it's like, okay, maybe you could do some sort of image detect, like you can use text recognize and then see if it says camera offline, maybe. But we could also do something simpler. If you look at this image, we can see that it's mostly the same color. It's mostly this shade of gray. And so what we're going to say is that we get one example of the frame that we want to delete, and then we can actually just extract the median pixel value. So we just we tally up all the pixel values here, and then we just take the median one, and then we get something that looks like this. So here's how we're going to turn those URLs now into actual pictures. What we do is we import the, as I did a slide or two ago, we import the image from the URL, and then we say if that failed, if we don't have an image, or if we do have an image but that image has the same median as this, then we ignore it. We return nothing. Otherwise, we add we sort of replace the snapshot with the actual picture. We are making like a sort of assumption here that if a image has this median, then it's bad. It's not impossible, because the UK can be quite gray. It's not impossible that we get like an actual image that's not this, but it has the same median. But it's extremely unlikely. There's quite a few decimal places here, and I think it's very safe to say that if we have this exact shade of gray, then we can get rid of it. So I won't run this because I've done it earlier and have it already done. It takes a minute to download all the pictures, but this is what we're using to turn the URLs into a picture. Okay, so where are we? We're at the situation where we have names, a picture, and the latitude and longitude. We now want to turn those pictures into what we're really interested in. The reason we got those pictures is because we want to know how many cars is in that picture. So how do we count cars? How do we count cars in a picture? Typically, this would be like a big computer vision task, and I wouldn't know how to solve this in general. But in Mathematica, we have this thing called image bounding boxes. Image bounding boxes. It takes a picture, which is it could be a frame, and then it looks for certain things. There's like a whole. It can look for like cats and dogs and other things as well. But what we're doing is looking for cars and buses. So this is going to take the snapshot, find the image, all the bounding boxes of the cars and buses. I set some options that I found work well. The target device and the GPU, that makes things faster. And then I just count the number of bounding boxes because I don't care about the actual bounding boxes. I just care about the number. But I've done that already and saved it in a compressed form. So this is how our data looks now. I've kept the snapshots for now, but this is how we look. We have a position, we have the name, we have the snapshot, which will drop in a second. We'll keep that for a traffic map, and then the number of cars that it counted. Good. This is looking pretty good, and we're already in a situation where we can build a traffic map. So here's some code that does that, and I will talk about it as it learns. So we have what we're going to do is do some geographics, and for each data point that we have, which has an associated position, we're going to drop a geomarker. A geomarker is like one of these pins that you see here. So a geomarker at the position of the camera makes sense. It's going to be colored according to the amount of traffic that we have, scaled from 0 and 1. that's basically this thing here. I say I'm doing the temperature map, which is I think a standard choice here, and I'm computing the maximum log value, which I'll explain in a second, but the maximum log value of all the traffic. So this is going to be 1 for the busiest intersection. Doing the ratio, and then I'm tooltipping it. So this geomarker, I'm tooltipping it with the picture, and I'm basically just mapping that over our data. So how does that look? Here's our picture of London, and we've got the tooltip. So if you mouse over, we can see the reading of the junction, and the color tells us how busy it is. So this is good, right? Because I mean, it's already a traffic map that's interactive, etc. But it lets us check that we're doing okay so far. So if I look here, this is the most red one. It looks very busy. If I look at some blue ones, they're empty. If I look at things that are somewhere in the middle, then they appear to be somewhere in the middle. So our numbers are roughly correct. So it seems. Why do I take the log? This is just like a general thing. Log scaling is a general technique, right? Where you basically have some exceptional values in the sense that maybe you might there's loads of times where you have a graph that looks like this. Goes from 0 to 100. So it's basically you have like some exponential difference in your highest and lowest things, and this graph it tells you exactly what's going on, but it's also at the same time it's not very useful, right? Because it's you can't see anything that's going on, and then suddenly it's gone past you. So in cases like this, it'd be useful just to take a log scaler, because then you can sort of see the nuance in the spectrum, but like at every level. So that's what we've done here, basically, just so we can get like a spectrum. Jim has asked a good question, and this is, and I'll take this opportunity to point out the failings of our method. Jim asks, does it recognize northbound versus southbound lanes, for example? No, it does not. If we look at the busiest picture, it's actually not that busy if you're going along the left-hand side here, right? This is why I was sort of careful to point out that what we're doing is minimizing the number of faces we see, not our transit time. Now, if we wanted to solve like the transit time issue, like how could we do that? It would be quite sophisticated, right? But we actually have the bounding boxes, and if we go and look at the original data, right? We have a video, so there's a JPEG, but there's an MP4. So if you wanted to be extremely sophisticated with the data that we have, it is possible to do what Jim is suggesting. See the motion of bounding boxes and then figure out your motion for that junction, and then you do that. That would make this talk a lot longer. So this is essentially why I have not done that. It is a good thing to point out, though. And yeah, so one improvement would be to go from the video and then recognize north versus south and your direction and stuff like this. We haven't taken into account the direction here, but maybe that can be an exercise for the reader. Okay, so I claim that we've already got an impression of the traffic at London. It's not perfect, as Jim has pointed out, but we know that there's lots of cars here and there's not that many cars here, etc. So we've addressed the first half of the question, or at least addressed it as much as we're going to today. Now we have to address the second part. How do we develop a model of the structure of London in terms of roads and intersections? We're going to do this with some image processing. So first of all, we need to know which part of the world are we interested in. So what I've done is what I'm doing is finding the maximum and minimum latitudes and longitudes. I'll just break this line down a little bit. Remember we have these positions, right, for each data. So this is the position of our first data point, and this is the latitude and longitude. So what I'm doing with this first is extracting this list. So that will give us the latitude and longitude. So we're going to have like a list of lists that look like this. We're going to have, the first latitude and longitude, then the second latitude and longitude, and so on. What I want is the minimum. Well, for a start, what I want is the minimum maximum latitude. So what I'm going to do is transpose that list. So now I have all of the latitudes in one list and all of the longitudes in another list, then take the minimum and maximum. And then basically from that, we get a bounding box. This is the bounding box that bounds all of our cameras. So we want to fix this for two reasons. One is just so we draw the part of London that we're interested in, where the cameras are. But secondly, we're going to do some rescaling in a moment. So we're going to, we'll cross that bridge when we get to it. Anyway, we said we're going to do some image processing to find this graph. So we need to start with an image. In Mathematica, you can just say geographics to get an image. So let me just run this line, and then I'll explain the code. Geographics, we're interested in London. I'm going to say, don't give me the street map. Don't give me the street names. Why? Because we already have the street names we're interested in the data, and that's going to add some stuff to this image that we don't want. All we want from this image is the structure, which you can sort of already see. So give me a picture of London without any labels, and put it like sort of in this box. So this is our picture of London. Now we want to pull out the structure of like the roads of London here. So what's the strategy? What we're going to do is we can see that the roads have like the same colors, like they have colors that are close, right? There's like these orangey colors, those are the major roads, which is not far from the brown, and then we have the blue of the Thames and stuff like this. So what we're going to do is try and sort of threshold or pull out the roads which have these colors, and then we'll turn that into a graph. So how do we pick the colors? There's a few ways to do it. We could use Mathematica has like that kind of like in Paint, where you can just click and it gives you the color value. We can do that, but we can also use this function called dominant colors, which will essentially do that for us. So we're going to take this to mean our roads. And then we do this. And this, I'll run this first to see the final product. This is the final product. We have a mask of the roads, but I'm going to break it down bit by bit. So London here is this picture. It's maybe confusingly named, but it's the picture of London. And I'm saying I'm interested in stuff that has this color. So if I run that, it's kind of, energizing each pixel proportionately to how close it is to that color. And we can see that our roads now are basically, our roads are bright, right? They're close to 1, and everything that's not a road is sort of close to 0. So we're going to try and threshold or draw a line. We're going to say the stuff that's bright, we round to 1. The stuff that's not bright, we round down to 0. We don't want to keep it. That's thresholding. In Mathematica, that's called binarizing. What I do instead is this thing called morphological binarize, which is very similar to binarizing, but it has this idea that like neighboring pixels are sort of related. Like pixels want to bring their neighbors with them. Normal threshold binarizing, that considers each pixel independently, and it says, okay, if it's above this threshold, then it's 1, otherwise it's 0. But here we're going to say, if it's above this threshold, or if it's not, if it's a lot of its neighbors are close to that threshold, that kind of thing. But basically, it keeps this idea of like connection. So okay, let's do that. So morphological binarize. I have to copy and paste to get. We're good at typing. Okay, so we're already pretty close, right? There's just some noise. There's 2 kinds of noise. There's like a positive noise, these dots, and a negative noise, stuff that's missing. So the positive noise is pretty easy to get rid of. We just say delete small components, and small components are gone. Now this negative noise, we're going to do some sort of closing operation, which is a very standard thing in image processing. And basically, we're just saying if something is close, we pick a particular matrix. It doesn't matter. But if you can see, like, there's this gap here. If something's close, we're just going to close things around, close gaps. Basically, we're just closing gaps, and that's what we do. Okay, and it's not completely perfect. We can see, like, for example, this should probably be connected, and there's like islands which we don't know what's going to happen, but it'll be close enough. Now, here's the really difficult bit. We have now an image. what we want to do is go from this image to a graph. How do we do that? To be honest with you, I have no idea. I have no idea how this works, but there's this function called morphological graph, which takes that picture, which is a mask, and then this turns it into a graph. You may notice this thing has like a blue box and this thing has a purple box. The reason is this is talking about two different things. This is an image. This is a graph. So it's drawn for us now as a, it looks like an image, but it's much more than an image. It's a structure. This is the structure of London. And we're beginning to get there. Okay. Now, what we want to do is put this graph on London, okay? There's all these junctions, they'll identify junctions, and you want to put that on London. This will be a little bit of a challenge. I invite you to think about how you do this yourself, because I may not have done it the best way. And in fact, that goes for anything that I do today. So we'll go through this and then pause for questions and then continue. Okay, so roughly there's two worlds. There's the world of latitude and longitude. This is the world where our cameras are currently living in. Each camera has this geo position, right? It has a latitude and longitude. Okay, and then there's the world of this graph. This graph does not have a latitude and longitude. This graph has X and Y coordinates, basically. And we want to reconcile these two worlds, right? We want to know what is the latitude and longitude of this node here, given its Cartesian coordinates, for example. And we want to do that for all the other nodes as well. Here's the strategy. Here's how I propose we do this, although, of course, you may have a better idea. Let's say that London has, I think it's much less than this, but let's just say London has 5 degrees of latitude across, east to west. It's 5 degrees of latitude. And let's say a camera is roughly a third of the way along that width. Then probably it's a third of the way along this graph as well. So, this graph is in a different world than, the actual world of latitude and longitude, but we're basically just going to rescale that graph. So to do that, first of all, we need to know where the nodes live in this graph in terms of their coordinates. So we can get that with this thing called graph embedding, which gives us, in the image that we just of the graph that we just saw, it gives us the coordinates. And I reversed them because, and actually I think I just got this wrong when I was describing this. I reversed them because latitude is north to south, right? So we're going to go YX rather than XY. I always thought like latitude, because it's, lateral is like sideways, that it should be east to west, but it's actually not. It's the other way around. So I reverse them and I get the Y and X coordinates. So this is the Y and X coordinates of the first node, Y and X coordinates of the second node, etc. And then I get the bounding boxes of those things. So this is why I got the bounding boxes of the cameras earlier, because I want to just basically rescale these two boxes so they're on top of each other, and then we're done. So here's the range that we encountered earlier. And then we have an expression that might look a bit scary. I'll break it down very briefly. So what I do is, okay, I have these Y and X coordinates that they are translated from 0 and they have a certain size. I'm going to rescale them. So it starts at the origin and it goes from 0 to 1. I'm basically going to normalize them and then reinflate them according to the geographic range instead. So let's break this down. We're looking here, let's say like a Y coordinate, and I want to translate, because like this starts at 0.5, 0.5. I'm going to translate it so it starts at 0, 0 by subtracting the minimum here. So subtract the minimum, and then I normalize so everything's in between 0 and 1. This gives us the the entire range of the Y values. I scale them so it's between 0 and 1. And then I sort of rescale them so it's now in the same range as the geography. And then I retranslate so it's it starts at the same place as geography as well. This is a function that does that, and maybe it's intimidating. I myself, I'm not sure if that's correct. So we want to check. So here's one way to check it. What I've done here is said graph to lat long at embedding. This is a so-called map apply. So embedding, it's our y and x coordinates for the first second node of that graph, first second intersection. And I want to apply this function because it takes the first and second thing. I want to apply that function to everything in this list. So that's what that looks like. And then I wanted to check that, okay, I hope that the nodes in this graph end up on this map roughly where they came from, right? I want to look and check that these nodes are actually corresponding to junctions. And it seems like they are, but actually we can do even better. When I wrote these slides, I didn't know about the existence of this thing called geograph plot, which seems like a niche thing, but it's, as we're about to see, sometimes very useful. So geograph plot plots a graph where all the nodes have a associated latitude and longitude. So basically we're going to start with London graph, but we want to do a vertex replacement. We want to replace the vertices with the kind of geo position. So it's vertex replace of London graph. And the replacement I want to make is this. I'll explain this in a second. Spell. Very good. I want to replace the vertices of the graph, right? So that's the vertex list of London graph. I want to replace that with the translated embeddings. So in translated embeddings, the first element, it's a list. The first element is the geo position of the first junction that we've calculated. So that's translated embeddings. I say normal. This I think is really good news. I think this shows us that we've done something. We've done okay so far. Like this graph is not completely 100% perfect, but it's definitely telling us about the structure of London, right? The nodes are where the junctions are, and the roads are where the roads are. Okay, the road doesn't seem to follow the curve, but it never was going to do that anyway. And anyway, we didn't actually mind about the curve. We just mind about which junctions can you get from other junctions. I always find it cool when like maths works out, right? Like here was like doing some maths. It's not extremely complicated, but it's maths, and it works out. Like here's the fruits of our labor. There we have from a picture of London, we've got abstracted not only have we abstracted a graph because that was quite easy, but we also understand where the nodes of that graph are. Okay. So that's good. We now want to actually convert nodes to geopositions, or do we? This is what I thought at first. It's like, okay, we have our nodes. We basically want to do what we just did and translate. Go from the Cartesian world, the X and Y world, to the the geographic world. Here's what I do. Here's what this looks like. Association map. So what association map does, let's just, because it's quite a useful thing. If we association map a function of a list, and it gives us an association that goes from the the domain to the range. It goes from A to the function applied to A. So this is going to go from the Cartesian world to its position in the real world. Okay, at this point I realize I've made a mistake, and it's not actually the last mistake I'll make today. What I'm doing here is going from nodes to geographic positions. I'm kind of going from the graph world to the camera world. But we have more nodes, more junctions than cameras, right? We have about like 100 more nodes than cameras. So I'm kind of like squishing, in a way, conceptually, I'm squishing our nodes into the cameras, where it'll be more comfortable to kind of go from our cameras and just see where they fall on the graph. So this might be worrying, like, do we have to do all that again? No, we do not. We can actually basically just flip these arrows. I'm saying if this node goes to this position, then that this position goes to that node. So I have to do this again. That just flips the arrows. And I wanted to just show briefly this resource function that I use all the time. It's not mine, but I use it very often. Show definitions. Because you might wonder, okay, how does this function work? How this function works is not very complicated, but it requires knowing some Mathematica. So what we do is we take the values of the association, the right-hand side, and the keys of the association, the left-hand side, and then we thread them together. So we put them next to each other, and then we just draw the arrows the other way, basically. Okay, so that was one mistake I made, and then I make another mistake. This other mistake is a modeling decision. What I say is, what I've been saying so far, is that we want to match cameras to nodes, right? We have cameras, we have nodes, we want to be able to put the cameras on the nodes. We want to match them up, so to speak. But this isn't true. And I'll reveal why in the next slide. You're welcome to think about it in the meantime. What I will do for now is continue with what I was doing, just I suppose for your culture. But this slide I'll go through fairly quickly because it's a bit technical. And as I say, it's also the premise is not quite the best premise that we could have gone from. But feel free to ask questions. Feel free also to wonder instead, like what is the mistake that I make when I say I want to match cameras to junctions. Okay, so anyway, I'm going to, at this point, obviously I hadn't realized that this was wrong. So like, okay, I want to match cameras to junctions. What I could do is just take, the closest camera and junction, then put them together. And then the next, out of what's left, the next closest camera and junction, put those together, etc. This is a so-called, in computer science, this is a greedy approach, where we locally make the, we locally make the best decision that, that at that time. But if we act locally, we don't get a globally optimal solution. We can see here that there's quite a few candidates. Like for this node, there's quite a few candidates that are close to it. So we have to make a decision, and we're making decisions locally. We're not guaranteed to get to a globally optimal solution. So for this slide, here's what I want you to imagine. Complete graph. So let's say we have only 5 cameras and 8 nodes, 8 junctions where they could go. So 5 cameras, 8 nodes. I want to match the cameras to the nodes in a way that minimizes the sum of errors, right? We're saying we know that this camera is roughly at this latitude and longitude. And this node, we've inferred that it's at a different latitude and longitude. And we want to minimize the sum of total errors. So in this graph here, imagine that each edge is labeled with a weight. The weight being the error, the difference in space between this camera and where we figured out that this node is. What we're doing now is looking for a matching. So this is the second graph that sneaks out on us. A matching is an edge for each camera that minimizes the total weight. So as I say, we'll go through this a bit quickly because it's technical, and also it won't be part of our final solution. So okay, we want to build this graph essentially, and then we're going to use, so this matching problem is like a well-studied problem in computer science. It's something that we know how to do. It's something that Mathematica has algorithms for. We want to build this graph. We want all the nodes, all the cameras, all the junctions, and all the distances between the cameras and the junctions. So here's where we start from, a distance matrix. A distance matrix is going to have, in one dimension, the position of all of our cameras. In another dimension, the position of our junctions, but in terms of latitude and longitude, and the value of the matrix at a camera and a junction is the distance between those two things. But what do we mean by distance? If we look at the first thing here, we see that we actually have like a quantity. Input form, forgive me. We have a quantity, this thing, it's in miles, and we want to kind of get rid of this quantity. So one way we could do that is just to say drop the quantity. But before we do that, we have to check that everything is in the same quantity. In the sense that if one of our entries was in kilometers, then we can't just drop that. We have to like translate between the units. But as it happens, we only have miles. So here's what we do: we drop the units, and then what we want to find is the minimum matching, the minimum weight matching, right? The edges that minimize the error. But Mathematica only has algorithms to find the maximum weight matching, which is no big deal. We can just negate the magnitudes. We negate the magnitudes, and then what I do, just to keep the values positive, because Mathematica seems to prefer it, is I add a constant to every edge. This will change the value of the optimal solution, right? But it won't change the optimal solution itself. It'll add, because every matching in this case will have 5 edges associated with it. So we add a constant, we add 5c, but we don't change the value of that matching. Okay, so this is our distance matrices. These are distance, and we're now trying to find the maximum matching because we flipped around. And just to check, so we have a number of rows associated with the number of cameras that we have, and the width is the junctions. Okay, as I say, I'll go through this quite quickly. We have this distance matrix. We want to build a graph. So what I do is make the matrix square, essentially, and then I say weighted adjacency graph. And then this is it. We have a graph. It's a big graph, more than 500,000 edges. I want to check that it's bipartite. What does that mean? Our graph, we were trying to make it look like this, right? Bipartite, it comes in two pods. So it's a sanity check, making sure that our graph is bipartite. It is bipartite, that's good. And now we want to find the maximum weight matching in that graph. So how we do that in Mathematica is we say find independent edge set. We run this algorithm. It takes a small while. In the meantime, while that runs, Jim has asked a question. The camera seems to be measuring the path between the nodes, which is better because the number of cars at an intersection depends on the state of the traffic lights. Jim, I think you're very close to discovering the mistake I made, but not quite. But you'll get but you are very close. Anyway, here we have now a matching. But at this point, at this point I wasn't sure, because if you look at the documentation of find independent edge set, it says that it works for weighted graphs, but it doesn't promise that it finds the maximum matching. So why do I think it finds the maximum matching? Because for 2 reasons. The first is because there's a deprecated function, bipartite matching and cover, that promises that it gives the matching with maximum weight, and also says that it's been deprecated by finding the independent edge set. So that's one piece of evidence. But another piece of evidence is that we can check if the matching is good. So our matching has weight this much, and so what I'm going to do is generate 200 random matchings and look at the heaviest one. It's quite a lot lighter. So this is very good evidence, I think, that even if our matching is not the biggest one, it's not just giving us any matching, because it's unlikely right, that it would be 200 experiments. Okay, so then I build the vertex weights. The vertex weights, in general, it points. So we say like the fifth vertex goes to the amount of traffic that thing got. And now we can start to build our first map, our first traffic map algorithm. So that seemed okay, but I noticed like later on that this matching wasn't very good. Although it's optimal, it's also not very good. So now I'll say what I did wrong. And it's what Jim was close to. If we go to where we built the traffic map and we look at the the cameras, we see that a lot of them are actually on a junction. This one's on a junction. This one's on a junction. This one is not on the junction, right? Neither is this one. And there's quite a few here. None of these here are at a junction. I made a mistake, right? A poor modeling decision when I said we want to map cameras to junctions. The fact is, cameras don't map to junctions, not all the time, right? Sometimes they're on a road and there's no junction. What is the consequence of this? These cameras are going to be competing for a junction, right? And one of them is going, because we're matching them to junctions. So one of these cameras is going to get that junction. And then now all of these other cameras have to find somewhere else to go. So they're going to compete with some other cameras at other junctions, which themselves may not actually be at a junction. And all of these cameras that are on this road are going to end up somewhere else at some other junction. And it basically is going to mess up our whole matching. That modeling decision is going to mess up our whole matching. So we have to do something else. What can we do? There's probably a lot of things that we could do. If you have an idea, you can say. All I'm going to do is say, okay, I'm just going to, for each camera, just associate it to the node that is closest to, the junction that is closest to. And then there may be collisions. That's fine. We're not going to say just one camera gets that node. We'll just add up the traffic. So we've already found like an association that gives us, that basically groups the cameras by the nodes that they're closest to. And we're just going to sum them up. We're going to say, okay, if the camera is closer to this node than any other node, we just add its traffic to that node. So I said we already did that. Let's just look again at what that looks like. We calculated this earlier on. It goes for each node, it points to the cameras that are like closest to that node than any other node. Right? Sometimes there are collisions, sometimes there's just one, and a lot of these nodes are going to be missing because they're not closest to any camera. So this goes from a junction to the cameras that are close to that junction. I want to replace these cameras, right? The position of these cameras with the traffic at that camera, because that's what we're really interested in. What I want to do is, so this geo position corresponds to a camera. This camera also has some traffic that we've already counted. I just want to replace the geo position with that number of cars. Then I want to sum up the stuff in this list. So that's the strategy now. So, okay, I want to go from these geo positions to the number of cars that have been assigned already to a node, an intersection. So how do I do that? There's a bunch of ways to do that. Here's what I'm going to do. We have our counter data. This is what we started with, right? This is what we started with. Just take this, and again, it looks like this. This is the first thing. We have this geo position, which is what we want to start from here, and we want to go from this geo position to the traffic. So what I do is build an association that goes from this position to this whole thing. I think I could have gone straight to the traffic, but what I did is I went from this position to this whole thing. So this is what this is doing. So this is what this is doing, and then this looks a little bit confusing. This is a map of a function over this thing. What does that mean? So this first map here applies this thing to every list, and then this map will like fall through. So basically, I'm applying it on the second level. I'm just turning all of these things into like this whole data point. So this is what this looks correct. We now have the nodes point to the whole data point now, rather than just the position. So that's what we've done there. We also want to go, so we want to go from these things to the traffic. So we're going to go from the values to the traffic, but we also want to go from the keys here to the vertex itself. We want to, at the end of the day, what we want to do is say the fifth vertex has one car there, or two cars there. So what we're doing now is associated thread embedding to this range here. What does this mean? Remember, the first thing in the embedding is the first vertex. So we're saying the first thing now points to number one, the second thing now points to number two. So that is going from the keys now to our vertices. Okay, so I was like, okay, that's good. Let's go. Let's turn the keys into vertices. But we see an issue. It says key absent. What does this mean? Like it says it can't find this key. When I went from the embeddings, I made a point to the vertices, but it says it can't find this thing, and it's because the nearest has somehow wrapped it up. It's wrapped it up. What we want to do is peel off this first list. So we don't want to map our converter over the keys. We want to map our converter, but first we take the first thing. So now this looks better. This vertex is pointing to the things that are close to it. And this vertex is pointing to the things that are close to it. And vertices that are close to nothing are not present in this list at the moment. So that looks correct. Now, as I just said, some vertices are going to be missing from the left-hand side here. Because some nodes are just not close to any cameras. So there's a little trick that I'm going to use to get the list that we want at the end. What we want in the end is a list where the first element of that list is the number of cars at the first vertex, and then the second element of the list is the number of cars at the second vertex, etc. What we want is a list like this. And we have here, at the end, we'll have like 320 goes to 1. So we'll have something like this. We'll have a list like this. 320, the 320th vertex has one car, and then, I don't know, the fifth vertex. Okay, let's just make this a bit smaller for now. So let's say the 8th vertex has one car, the 5th vertex has 5 cars, the first vertex has 8 cars. We have something like this, and then there's some vertices missing, the ones that aren't close to anything at all. But we still want to set those to 0. So here's this trick. And there's, again, everything I'm doing, there's a bunch of ways to do it, but here's a trick. We can use this thing called a sparse array. I want to just pause for a second to talk about what a sparse array is, because this is something that's very useful, even outside of this webinar. It's just very good to know about, and it's like an idiom that happens in programming and in computer science. Let's say you have a list that's 1 billion elements long. This is possible. There's lists that are that long. You have a list that's 1 billion elements long, but this list is mostly the same. Right? There's a few exceptions. For example, the 8th element of that list might be 1, and the 5th element of that list might be 5. But everything else in that list is 0. So this is called a sparse array because it's sparse. It's kind of empty. How do you store this in memory and work with it as a computer? The normal way, right, with an array like in C, is that you allocate memory for 1 billion integers, and then the 8th element is 1, the 5th element is 5, the first element is 8, and every other element is 0. So that's the normal way to do it. What you could do instead is just remember this. You remember the exceptions, or the parts of the list that are different, and then you remember the length of that list, and you don't remember anything else. You don't allocate 1 billion elements. You just say, okay, if the element I'm looking for is in our list of exceptions, then we take the exceptional value. Otherwise, we know that it's 0. So that's a sparse array. The point is, though, mathematically we can convert that into a normal array, and this is how it would look like normally. The point is, we've done what I said we wanted to do. The elements that weren't here on the left hand side have been given a value of 0, and everything else is in the correct place. So this is basically what I'm doing. And now, again, we can do this from this is the same thing as earlier on. We can see, I want to do 1 plus here, I guess. We can, yeah, good. We can look at the traffic in London. We can ignore this thing for now. We're using this later on to draw our to name our nodes. Okay, so let's reflect on where we are right now. We have a graph, and some of the nodes in this graph, we have a number of cars associated with them, right? Those are the ones that were close to cameras. If it was closer to a camera, it got the traffic from that camera. But how do we sort of interpolate the traffic that are at nodes with no cameras? Because if there was a node with no camera, what we could do is assume that there's no traffic there, but that's probably not a great assumption. We know that there's some traffic there, and we know that the traffic at that node will have something to do. We'll be able to make a decent interpolation from the nodes that we do know about, the nodes that have cameras close to them. So again, there's a million ways to do this. How do you interpolate over a graph? There's a million ways to do this. What we're going to do is do like a little simulation. We're going to simulate the motion of traffic around London, which seems like a big undertaking, and maybe it is, but it will turn out to be just a bit of linear algebra. And the actual linear algebra we don't have to go through in detail. I will just tell you what's going on. Here's the assumption that we're making when we do the simulation. If a node has 9 cars, 9 cars at that node, and 3 exits, then in a step of the simulation, we're going to say that traffic sort of goes out, it diffuses uniformly over those edges. So if you have a node of 9 cars, 3 exits, then those cars will go 3 each on each exit. It's an assumption. It's not a perfect assumption, right? It's more likely that they're all moving towards the center or something. And you could account for this in what we're going to do. Yeah, this is how the simulation will work. And we're going to use the so-called adjacency matrix of the graph, which we've seen already. Before we do this, I want to point out to a similarity, because someone has asked, like, are the concepts here used elsewhere? So this thing that we're about to do is very common, and it is in fact a long time ago how Google used to work. Google search used to work. Now, what could possibly be the similarity here? Because these seem like completely different domains, right? We're simulating traffic and moving around a graph of London, but I'm also saying this is how PageRank used to work. How PageRank worked is like this. It's you want to know how important a website is. Okay, you can say, okay, a website is important if it's linked to by other important websites. The analogy here, by the way, is important means lots of traffic. So if an important website points to you, then you are probably more important for that. If a lot of important websites point to you, then that makes you more important. But at the same time, if a website points to lots and lots of different things, right, then each citation is less impactful, right? If there's a website that points to like a billion other web pages, then we want to kind of not consider those citations very bigly, right? Because there's lots of them. They're quite cheap. So what we're doing, in a way, is dividing the contribution of a node or a vertex by its degree, by the number of edges. So, and this is what we're doing here now as well. We're saying, okay, a node in this graph will draw from its neighbors, right? And as we go through a time step, it will draw from its neighbors proportionate to the weight of those neighbors. So the traffic of at a junction, or the the status of a website, but inversely proportional by its degree, right? So the core of the algorithm here is the same, although these are two very different things, and you'll see this elsewhere as well. This is just a way to sort of determine status in graphs. So again, this is technical. Feel free to stop me and ask questions if you'd like, but I also don't want to be too boring. So that's the setup here. That's the actual simulation we're running, even if it doesn't look like it because it's just a few equations and there's no interactive simulation. But it is what we're doing. We get the adjacency matrix of the graph. So this is the adjacency matrix, roughly, very hand wavily, is talking about neighbors. It's talking about which junctions are connected to which other junctions. And then we're scaling each junction inversely by the degree. So we're saying, okay, if a junction has a lot of exits, then it doesn't give as much traffic to its neighbors, right? Because it has a lot of exits. It's giving a lot of traffic to its adjacent neighbors as well. So check the dimensions, the things are working correctly. And then I just run the simulation for 3 steps. I take the propagator, I take it to the power 3, and then I multiply that by our state. So we're drawing from our neighbors, and then drawing from our neighbors again, and taking the ceiling. So that, although it doesn't look like it, I promise was a simulation of traffic around London. Okay. Now, how are we actually going to solve? I mentioned already like a shortest path. What we want to do is find the lightest path. We're giving weight to parts of our graph. This weight is the number of chords that we know are there, and we want to take the lightest weight path. But what we've done so far is given weight to vertices, right, not edges. And the shortest path algorithms that we have work with edges, not vertices. So, okay, we have like another problem. How do we if we know that there's 5 cars, we know that there's 5 cars at a junction, and then I don't know, like 7 cars at some other junction, then how many cars are in between those 2 junctions? For lack of a better idea, I suggest we just take the average. So 5 plus 7 is 12. So I say, okay, that edge has 6 cars. If one end of that edge has 5 cars, the other end has 7, then we add 5 and 7, divide by 2, get 6. And that's what this line here is doing, essentially. So I take a random sample just to check that we're getting roughly what we expect, like numbers. It's just good to look at random samples every now and then, because Mathematica is very powerful, but it can also be a double-edged sword in the sense that, like, okay, if you ask Mathematica, what is H? Let's put O. What is O? It's going to tell you that O is O. In Python or in C, if you ask what is O, it's going to like crash and say, I don't know, you didn't define it, or maybe you defined it, but you didn't initialize it. In Mathematica, it just says O is O. So this is really great if you're doing maths, right? Because this is what we do in maths. We say, let V be a vertex, for example, and blah, blah, blah. But it's not great if you meant to define O, but you forgot, or you defined something else, and there's an error. What Mathematica will do is very happily continue processing what with O instead of what you meant. So it's good to check that things have evaluated in the way that you expect. So we have numbers here. There's no O's or anything that I've forgotten to define. Like, for example, I don't know, if I as an example, if I said mean of a lowercase m, there's no error message, right? But this now looks very different. So that's the kind of thing that you want to check. We do actually want that back. Okay, so we're getting towards the end. We have a graph of London. The roads are weighted according to the cars that we know are there. We can start to look. We can draw our last sort of traffic map of London. It's busy towards the center. It makes sense. Now we want to know we wanted to find shortest path, right? So how do we do that in Mathematica? like this is like a theme now in Mathematica. If you want to find the shortest path in a graph, you just say find the shortest path. You don't have to know about Dijkstra's algorithm or any other algorithms. You just say find shortest path, and then it'll find the shortest path. So here we pick two random places, and then I said find the shortest path. That gives us a list of vertices, right? But for us, that's not very useful because these are just numbers. So we can draw it on our graph of London, and we can see that we're now avoiding the busy bits, right? We're avoiding the busy bits of London. And we can, this is random things. We can keep going, get random paths. But in Mathematica, it's pretty easy to make like a little interface. So we say manipulate, basically. So I'll talk briefly. We're almost done, but I'll say a little bit about how manipulate works. Manipulate, what it does is it takes an expression. So here's the expression. We're saying the path is the shortest path between P1 and P2, but we don't say what P1 and P2 are. And then we highlight that path. And then the stuff that we didn't specify in the expression, we can specify in the second argument of manipulate. And we're saying P1, it starts at 23, and it's anything that comes from this matching. When we evaluate that, we have now like an interface. So this is the calculated shortest path, but we also have like some drop down of different roads. If we want to know, okay, what's the shortest way to get from, I don't know, north of Waterson to, I don't know, Christchurch Road, then there we go. And we've built like a little app. Behind the scenes, there was a lot going on, right? But we in the end, we built a little app. And that brings us to the end of the webinar. So just to summarize, while you guys think of any questions or comments or anything, I'll summarize roughly what happened. We set out a question, and then we realized quite quickly that a question comes in two major pods. How do we model London? There's like a modeling problem, and then there's accessing data problem, right? How do we get the data? How do we know which cores are at which nodes? How do we find out the nodes in the first place? So that wrangle, the JSON response was kind of strange, so we had to wrangle with that a little bit and deal with it, and so on. But we did that successfully. Explore, it was quite. Is the first thing we did before it got really involved is to build a traffic map, which is nice to be able to do, right? It's nice to be able to build a traffic map, even if we didn't yet find the shortest paths. We have like a traffic map and like a camera feed. Analyze, that was the whole thing with the shortest paths, and the communicate was that little manipulate expression at the end. Thanks. And yeah, in terms of data science, so this is like a little bit, it's definitely data science, but it's a little bit tangential, right? We didn't do any like linear regression or we didn't do any machine. Well, we used computer vision, but it was we used it as a black box, right? This is it's definitely data science, but it's a little bit tangential. But I think it's good to like know about a bunch of things. I guess this is close to like sort of classical computer science. But I think it's good to have these tools in your toolbox as well. Like, there's a lot more words that you probably recognize now, at least, and that you can go back to this recording, or whatever, or what to Google at the very least, if you come across a similar problem like this in the future.